Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today, we will continue our discussion on fundamentals of some of the operations related to image processing. In the last lecture, I discussed about segmentation of images, and we continue that discussion. In the last lecture, we considered a mixture model, Gaussian mixture model of an image, and finding the parameters of those mixture densities, we can partition the image into several segments. Today, we will discuss a very popular algorithms which is called k-means clustering, which is a more generic with a more generic objectives of clustering data points, and segmentation of image points or the feature space in the in the domain of the image. That itself is also a kind of partitioning. So that's why a clustering equivalently also clustering techniques can be also used for segmentation, and k-means clustering is a very popular and very simple technique for such data partitioning. So let us first understand the problem of this k-means clustering. We have, say, d-dimensional data points, say n d-dimensional data points in general, and so it is just data points. So there is no spatial ordering as we usually consider for an image when we represent an image, but any kind of set of data points. But there the objective is to compute k partitions, and each partition is also referred to as cluster. That's why the term clustering came. So we have to compute k partitions in them in such a way that it minimizes the sum of square of distances between a data point and the center of its respective partition on a cluster. So if I can mathematically represent this problem, and it's an optimization problem. So you are minimizing a sum of squared errors. Squared errors are taken with respect to the center. So you can see in this description, suppose you have the kth cluster, and suppose its center point is given by this ck. You can see that this is a partition of points, data points for the kth cluster, and you are considering average of all such data points. This is the cardinality of the set. So by the number of points in that cluster. So if we take the average, that is the center. So the distance from a data point which belongs to that cluster and its center is expressed by this norm, L2 norm. So this is basically, these are, say, vectors. So if I take the difference vector and we are considering its magnitude of the vector and square of that magnitude. So it is square of that distances, that is we are considering. Now, since there are all such partitions, so it is basically, I should say, k equals to 1 to k if I index these partitions. So for all such partitions, what is the sum of square of such distances? We call it errors. So this is the objective function, and we would like to minimize this error. So we would like to get such a partition which will minimize this error. So this is the problem of k-means clustering, and as such it's a very combinatorially explosive problem. So it's an usually NP-hard problem. If just if it is k equal to 1 trivially, you can always get the center. So for any value k greater than 1, it's an NP-hard problem. So that's why there are various heuristics based algorithm, particularly one very popular algorithm which is called Lloyd algorithm, by the name came from by the inventor of this algorithm. So and also you see that it's quite old. It's in 1957. And this algorithm, which is also referred to as batch k-means clustering algorithm, what it does that you can start with any arbitrary partition initially, and then for that partition you can compute its center. Then you assign a point to that partition which has the closest, whose center is closest to that point. So this is a part. So you will get a new partition out of this. So some of the points which in this iteration which belongs to say ith partition, but maybe it is closest to another jth partition. So we will be reassigning them. So during this process. So once you compute, so your center points will be changing. But if you iterate this process, it is expected that it will converge. It will converge to a center, and ultimately you are expecting that there is no change if it is properly partitioned. So all the center points should be within that cluster, and also those centers are also closest. So when you come to that conditions, and maybe a little bit of smaller changes you can tolerate, like 1 or 2 swapping, or maybe a few swapping you can tolerate. So then you can stop these iterations, and that is how the end result would be that partitioning. So I am just showing one example with 2 partitions, and we are also considering all data points in a 2-dimensional space. As you can see, I have shown those data points by just drawing some circles centering at the data points. So they denote those data points. So suppose your initial centers are these 2 triangles. Triangles are showing the positions of their centers, just to differentiate from the data points and the centers. And I am also using 2 colors to denote the class attributes of a data point. So initially, if you choose this center, and then you assign the class to a data point whose center is the closest, and if we do that, so you can compute those partitions and say these are the few things you will get. So the green colors data points are they belong to the same cluster of because the green center is closest to them, and vice versa. So this is my these partitions. Now again I will recompute the centers. So I will update the centers. So through updation it will move inside within that partitions, right? And you continue this process. You continue this process again. You relabel them and recompute centers. And once you continue this process through few iterations, you will find that actually these centers are coming within the partitions itself, and no more change is observed. So this is how we get the result. Now this is the principle of k-means clustering algorithm. But when you want to apply for images, there are various ways you can do. I will just show you one particular approach, that is how we can perform the histogram analysis using k-means clustering. In the previous technique, it is a histogram we have analyzed to find out the Gaussian component of the Gaussian mixture models, and then through that we are finding out the intervals of the brightness intervals for related to each component, and that's how the segmentation takes place using that brightness interval. So in the histogram analysis here, if I apply k-means clustering, which means in this case your feature space is just brightness value, so a single dimensional feature space, but histogram gives you the frequency or the number of points. So when you are updating a center, you consider that as the weight to that brightness model. So this is how this algorithm is developed. So what you can do, you can compute the histogram once again from the images, and then you can choose any arbitrarily initial Cray brightness levels for the set of means, like and if you are considering there are k such partitions, so k should be given. In k-means clustering, k has to be given. So that's a kind of hyperparameter of the algorithm. So you can choose certain means, and let us assume that these means are ordered in ordered some fashion, because that would help us in designing this algorithm in the computation. So you can order them in such a way that we choose them and we can order them. And then we can update the ith means, as you understand that whenever, since it's a very simple case, so in this case, if I consider any mean, say, so if I consider any two adjacent mean, say you consider a mean, say m I minus 1 and mi, say in your brightness interval, since they are sorted, suppose if I draw them, if I look at them, so this is the brightness axis. So as you understand that if I draw the perpendicular bisector, so all these brightness values, they will be closer to mi minus 1, and all these values, they will be closer to mi, and not only closer, they will be closest because of this ordering. So we actually use this principle to recompute the center. We did not we did not we did not go for computing the closest interval exhaustively, closest centers exhaustively. So this expression means that the new updated center would be like this. So you can see that the corresponding interval. So I am updating mi. So my the pixels associated closest to mi, or brightness levels rather closest to mi, should be between. So if this is mi, this is mi plus 1. So this half of this point and this half within this interval, all these pixels are, all these brightness levels are closest to mi. So only those brightness levels are considered within this range, and then they are weighted by their respective counts or frequency counts. So that is given by the histogram. So this is the weighted average. So this is the updated center. So this is what we go on doing for every centers, and finally when it converges, we stop. So that would give us the centers, and from the centers, as you understand that now intervals would be defined. So this is the interval. So once the centers are there, then you can easily compute the threshold intervals. So an example with the same image what we used in the previous example of Gaussian mixture model. Here also, suppose this is that image, original image, and as I mentioned earlier that to make the modes of histogram distinct, we will be making a contrast stretching by doing pixel mapping. And then in that case, if I use that histogram and if I apply that k-means clustering with k equal to 3, then these are the positions of the centers. So these are the positions what is being shown here: 39, 90, 147, approximately. I have just shown in this graph to show you in this plot. So if I from there, when we compute the intervals and apply them just for segmenting the images, with the level them. So I am showing the pseudo colored image of 3 intervals, and these are the intervals with respect to those means. You can find out. So the blue color is showing the result between 0 to 65 brightness levels, and as you can see that they correspond to the water of a river in this particular satellite image. And green is usually, this area is a forest area. So green is usually what we can associate with forest coverage, whereas yellow is a urban settlement. So this is some kind of rough characterizations of these intervals. So segmentation can really give you more information which was not very visible. So of course, in contrast stretching, you can see and you can associate with that. You can see that this is a settlement, and which is yellow, and the river is very perceptible. And this zone, you can see that this zone is coming as a green zone here. So